Okay, so it is the chapter 3, section 1, simple harmonic motion. But before starting the simple harmonic motion, we should first define what periodic motion is. So simply, periodic motion is a repeated motion. If the motion repeats itself, the object moves over the same path or over the same distance. So it is a repeated motion, periodic motion. For example, a child on a playground swing. So it is moves back and forth on the same path. So it is a repeated motion. Pendulum club is moving back and forth. It's a repeated motion. Acrobat swing on a trapezoid. So it's a repeated motion. So every kind of repeated motion is called a periodic motion. The simplest type of periodic motion is back and forth motion. Is the motion of the mass stretched to a spring. So when you connect a mass to a spring, such as spring, this is a spring, and stretch the object from this position, which is called unstretched position, and release it, it will start to move back and forth like this. So this motion is a kind of repeated motion or periodic motion. When the spring is stretched or compressed and then released, it vibrates back and forth around its unstretched position. So this is the position, unstretched position. You are going to stretch it a little or compress also. When you release it, it will start to move back and forth. If a spring is pulled with a force, the spring stretches, yes, or vice versa. If you push the spring with a force, the spring will be compressed. But when we stretch or compress the string, we observe that if we apply a force F, it stretches by a distance of x. So when you apply another force, which is 2F, you are going to observe that it stretches by 2x. So this is the case. Initially, the force is F, so it's stretched by a distance of x. This is the unstretched position. So when you increase the force by 2, also you are going to observe that it stretches by a distance of 2x. So if you apply another force 3F, you are going to observe that it will stretch by a distance of 3x. So however, the ratio of F over x, 2F over 2x, 3F over 3x, always the same, F over x, F over s, F over x. So this ratio, force divided by x, the ratio, force divided by x, gives a property, it's a property about the spring. So this property is called as the spring constant K. So when we divide the force applied on the spring to the displacement of the spring or amount of stretch of the spring or compress, so it is called the spring constant. This number is always positive, K is always positive. So when you cross multiply them, you are going to get that F is equal to K times X. This positive constant, K, measures the stiffness of the spring. Stiffness means how rigid it is. So how hard to stretch or compress a spring, we say that it's a stiff spring. So unit of the spring constant, as you see, is Newton divided by meter. Not hard to understand. K is equal to F divided by X. So F is Newton, X is meter. So unit of the spring constant is Newton divided by meter. If the K is great, so a greater value of K means a greater force is needed to stretch or compress the spring. Yani stiffness of the spring is high. So, okay, let's solve a problem. Assume that a mass of 0.55 kilogram attached to a vertical spring. As you see, this is the vertical spring. So a mass is attached to this spring. Of course, this attached mass will have a weight, gravitational force, Fg. And we can calculate the gravitational force as mass times acceleration of gravity. So mass is 0.55 kilogram multiplied by 9.81 is the acceleration of gravity. So the force applied to the spring is equal to 5.4 Newton. So this mass stretches the spring by a force which is equal to 5.4 spring. So applied force, the force applied is equal to 4.5 Newton. So it says that when this force is applied, the spring stretches 2 centimeters from its original equilibrium position. What is the spring constant? So x is equal to 2 centimeter, 0.02 meter in this case. So then we are going to calculate what k is. So F applied is equal to k times x. K is equal to F applied force divided by x. So F applied force is the gravitational force of the object, so 5.4 Newton, divided by stretch. Amount of stretch is 0.02. So when you divide them, you are going to get answer as 217 Newton per meter. Another question. A slingshot consists of a light leather cup attached between two rubber bands. So as you see, this is a slingshot. So one rubber, two rubber bands attached between, a rubber band attached between two, a leather cup. So this is a leather cup attached between two rubber bands. If it takes a force of 32 Newton to stretch the bands 1.2 centimeters, so we apply a force. Applied force is equal to F applied is equal to 32 Newton. So we are going to observe that it's stretched by a distance of 1.2 centimeter. So we should write it in meter, which is equal to 0.012 meters. So what is the equivalent spring constant of the rubber bands? Why it's asking equivalent? Because there are two rubber bands. For that reason, we should find the equivalent of them. So then F applied is equal to K times X. K is equal to F applied divided by X. F applied is 32 Newton, so we apply the 32 Newton force to this rubber bands. So we observe that it's stretched by a distance of 0.012 meters. So when we divide them, answer becomes 2,666.7 Newton per meter. Question 2. How much force is required to pull this leather cup in item 1? And according to problem 1, we are going to solve this one at a distance of 3 centimeters. So we found what the equivalent spring constant is. So it is 2,666.6 Newton per meter. So when we pull it, it's reached a distance of 3 centimeters. So x is equal to 0.03 centimeter. How much force must be applied to stretch that the leather cup? So F applied is equal to K times X. K is given as 2,666 times distance is 0.03 in displacement. When you multiply them, answer will be 80 Newton. So 80 Newton force is applied to stretch that rubber bands by a distance of 3 centimeters. So when a spring is pulled with a force F applied, and if we apply a force, as you see, this force is F applied, you are going to observe that spring is pulling your hand back with a force called elastic force. And you are applying a force to right and stretching the spring. By the time spring resists this force in opposite direction. This force is known as elastic force or spring force. This is the force because of the elasticity, comes from the elasticity of the spring or any elastic object. So the spring force, another name or elastic force, always pushes or pulls the object, right here it is pulls, towards the equilibrium position, and unstretched position. That position is unstretched position. As you see, the elastic force is pulling your hand or the handle back to the unstretched position. For this reason, it's sometimes called a restoring force. Why restoring force? It's called because it wants to restore the position of the spring to original position. So now, when you apply a force to right, as you see, F applied is to right, so it stretches the spring by a distance of x. So these two vectors are in the same direction. In mathematics, if the two vectors are in the same direction, the mathematical relation between these two vectors always written as positive. So F applied in this case is equal to k times x. However, if you look at the elastic force is to left, but displacement is to right. So then, because these two vectors are in opposite direction, mathematical relations between these two vectors will be negative. So in elastic force, because these two vectors are in opposite direction, will be equal to minus k times x. The mathematical relation between the x and F elastic is negative because F elastic is in the opposite direction of displacement x. So this force this force, when you release it, when you release the applied force, as soon as you release it, when you remove the force, the object will start moving, or the handle will start moving towards the unequilibrium position. For that, this force, this elastic force, mostly, generally, is called as the restoring force. So the magnitude of the restoring force, this restoring force is directly proportional to displacement. Yani if you increase x, magnitude of the F elastic also increases. Yeah, number. If you increase the number of x, number of elastic also increases. However, the direction of the spring force, or elastic force, or restoring force, all of them refers to the same force, is always opposite the direction of the object's displacement. As you see, the object is moving to right, so elastic force will be to left. If you compress the spring to left, so elastic force will be to right. So they will be always in opposite direction. So this relation between the elastic force and the displacement, which is F elastic minus K times X, is known as the Hooke's law. This negative sign, here this negative sign, shows that the spring force will tend to move the object back to its unstretched position, and always in the opposite direction. Elastic force is in the opposite direction of the displacement. By this way, it's trying to pull it to the equilibrium position. Now we are going to define the word simple harmonic motion as any periodic motion. Yes, simple harmonic motion is a kind of periodic motion. Every simple harmonic motion is a periodic motion. Any periodic motion that is the result of a restoring force. Yes, this is the key. There must be a restoring force in this periodic motion. It is described by the simple harmonic motion. And if there exists a restoring force in a periodic motion, that kind of periodic motion is known as the simple harmonic motion. Every simple harmonic motion is a back and forth motion over the same path. Back and forth motion over the same path. And every simple harmonic motion is a periodic motion over the same path. Better to say over the same line. An object must move over the same line, back and forth continuously. So then we say that this is the simple harmonic motion. The position of the object when the spring is unstretched or uncompressed, original position, is called the equilibrium position, right here, as you see. Generally, this original position is represented by x is equal to 0. No stretch, no compression. Then variation about in an equilibrium position, in which a restoring force is proportional to displacement is called simple harmonic motion. So that if the object is continuously moving about this point, right, left, right, left, right, left, right, left. So this kind of motion is known as the simple harmonic motion. Now let's answer some conceptual questions. For example, it says that the motion of the Earth orbiting the Sun is periodic. How do you understand it? Because it's a periodic motion. Earth is starting from here, going to Sun again here, once again, every year. So it's a periodic motion. Is this motion simple harmonic? Why or why not? This motion is periodic but not simple harmonic because the force which rotates the Earth around the Sun is the gravitational force or centripetal force. However, object's displacement is tangent to the circle. So, for simple harmonic motion, there must be a restoring force, and we know that restoring force always proportional to displacement. As you see, this force is not proportional to displacement. An object must move over the same path. As you see, this Earth is not moving over the same path, even though over the same line. So it is making a circle. It doesn't move back and forth over the same line. For that reason, we cannot say that this is not a simple harmonic motion. Question number 2. In pinball games, the force exerted by a compressed spring is used to release a ball. Now, yes, you are right. In this game, initially the spring is unstretched. Then you stretch that spring by a distance and put a ball here. And, of course, some energy is stored in the spring. And then release it. The ball is starting to move with a speed v. If the distance the spring compressed is doubled, how will the force acting on the ball change? If the spring is replaced with one that is half as stiff, how will the force acting on the ball change? Okay, if remember, force is equal to K times X. When you increase double the distance, you are going to double, of course, the force. But when you decrease the stiffness. Yani you decrease the k by 2, of course force must decrease by the same number because they are directly proportional. Yani f is proportional to k, f is proportional to x. So now let's study the characteristic of simple harmonic motion. Now remember we said that the object is initially at equilibrium position. This is called equilibrium position. But when you stretch the spring, of course it's connected to an object whose mass is m, from the equilibrium position by a maximum displacement, x max. So it will start moving back and forth over the same line. So at maximum displacement, the force becomes maximum. It's very easy to understand because restoring force or elastic force, let's say elastic, is equal to minus k times x. If x becomes maximum, magnitude of the restoring force also becomes maximum. So it's maximum. However, displacement if in positive x direction, so restoring force will be in negative x direction because of this relation between them. If force is maximum, yes, force is maximum, acceleration also will be maximum. How can I understand them? Because according to the second law of motion, if you divide the force acting on the object by the mass of the object, you will find the acceleration of the object. Because the force is maximum, acceleration also will be maximum. Don't forget, force and acceleration always changing with the same. If it is maximum, acceleration is maximum. If it is to left, acceleration as a vector will be to left. What about the velocity? Velocity will be 0. Why? Because object is moving back and forth. At maximum displacement, which means object cannot move to right anymore. Yani it stops. So then it stops and turns back. Yani without stopping, no object can turn back. For that, at maximum displacement from the equilibrium position, so velocity of the object will be 0. Now let's study the case where the object is at equilibrium position. So then remember, object is oscillating between x maximum and negative x maximum. This is the equilibrium position, unstretched position. If position is unstretched, if x is equal to 0, which means according to the Hooke's law, minus k times x, if it is 0, so force is 0. Force will be 0 because the spring is not stretched, not compressed. For that reason, force acting on the object will be equal to 0. As I said, if force is 0, acceleration will be 0 according to the second law of motion. But speed becomes maximum at equilibrium position because when you first stretch it to the x maximum and release it, so as soon as you release, it starts to approach and accelerate towards the equilibrium position. So it accelerates, which means speed increases, when it becomes maximum right here. So at equilibrium position, the speed becomes maximum and passes from equilibrium position with the maximum speed. But after passing from the equilibrium position, it starts to compress the spring again. As it compresses spring, and of course x increases, elastic force starts to increase again. Because remember, if F elastic is equal to minus kx, if x start to increase, elastic force also in numbers start to increase, but in opposite direction. So because the displacement is to left, elastic force will be towards the equilibrium position to right. At maximum displacement from the equilibrium position, so then which is the object stops there, so its velocity is 0. Of course, elastic force will be maximum because x becomes the maximum number. So elastic force also becomes maximum at this maximum displacement. Acceleration, yes, it's also maximum. Why? Because acceleration is equal to force divided by mass. If force is maximum, acceleration also must be maximum. So this is the general explanation of all cases. This is the general explanation. So at equilibrium position, at positive x maximum, at negative x maximum, so how does the restoring force, acceleration, and velocity changes? First, remember them. So at maximum displacement, velocities are 0. Why? Because objects must stop. Object must stop because the velocity is 0 in this case. At maximum displacement, right or left, restoring force must be maximum because elastic force or restoring force says that minus k times x. If x is maximum, yes, it's maximum distance from the equilibrium position, elastic force becomes maximum. If force is maximum, according to second law of motion, acceleration must be maximum at maximum displacement. What about equilibrium position? At equilibrium position, because no stretch, no compress, so force will be zero according to the equation. If force is zero, acceleration must be zero according to second law of motion. However, velocity will be maximum because when you release the object starting to accelerate towards the equilibrium position because speed increases and becomes maximum right there and starting slow down and stops there. So for that, as at equilibrium position, the velocity becomes maximum. However, when you compress or stretch a spring, we can explain the motion of the object by also using the energy. When you stretch or compress a spring, it stores elastic potential energy. This title normally started in the 11th class. When you compress a spring by a distance of x, so elastic potential energy stored in the spring is equal to 1 over 2 kx squared. Yani if you compress this or stretch the spring by x, there will be energy stored in the spring. So this energy, when you release the object, is converted to kinetic energy, and the motion of the energy of this object is coming from the elastic potential energy. Yani you compress it until this point, so because you increase the x the most, so then right here elastic potential energy becomes maximum, but when you release it, so it starts to speed up towards the equilibrium position because elastic potential energy decreases, and by the time kinetic energy increases. That's why it's passing from the equilibrium position with the maximum speed. Okay, so a stretch or compressed spring stores elastic potential energy. As once the bow string has been pulled back, this is the bow string is pulled back, the bow stores elastic potential energy according to the equation 1 over 2 kx squared. When the bowstring is released, as soon as you release the bowstring, the arrow leaves the bowstring and it gains most of elastic potential energy originally stored in the bow. So originally in the bow is stored elastic potential energy. When you release the arrow is starting to move. So as it's moving, it gains most of. Why most of? Because still some of the energy will be stored in the bow and bowstring. So most of the energy, elastic potential energy, is originally stored in the bow, is converted to kinetic energy of the arrow. Because the mechanical energy must be conserved, yes. What does this mean? Kinetic energy plus potential energy of bow and bowstring and the arrow system must be the same. The kinetic energy of the bow, arrow and bowstring is equal to elastic potential energy originally stored in the bow. Yani at the beginning when you stretch the bowstring right here, so all the energy is elastic potential energy. As soon as the arrow is released, so the total energy, the elastic potential energy decreases, and all this energy is converted to kinetic energy of arrow, bowstring is vibrating, and also the bow is vibrating, so kinetic energy. Is it possible to define the motion of an object connected to a spring by this way? Yes, we can. So when you starting to stretch the object more and more, because x increases, elastic potential energy also increases according to the equation 1 over 2 kx squared. And at maximum displacement, because x is maximum, elastic potential energy becomes maximum at the maximum displacement. But kinetic energy is zero because at the maximum displacement, what does it mean? Object cannot move anymore. So then object stops right there. So that's for that is kinetic energy is zero. Then object stops there and then turns back. As soon as object turns back, it starts to move towards the equilibrium position and accelerates. By the time the amount of stretch decreases and becomes zero. As the object is approaching to the equilibrium position, elastic potential energy decreases and becomes finally zero because at equilibrium position no stretch, no compression. By the time this energy, total energy, is converted to kinetic energy at the maximum, at equilibrium position, kinetic energy becomes maximum because the velocity is the maximum right there. However, later object passes from equilibrium position with that energy and starts to compress this time the spring. As the spring is compressed, this time x in the opposite direction, x starting to increase and becomes maximum. As the compression becomes maximum, elastic potential energy again becomes maximum by the time object stops. So its kinetic energy becomes 0. So this is the case for the simple pendulum, mass spring system. So in elastic potential energy, in a spring, in an ideal system, the mass spring system would oscillate indefinitely. What does it mean? When you set this system into motion, if energy is not lost, this system will oscillate back and forth, continuously, back and forth. So, however, in physical world, there is friction. Because of the friction retards the motion of the vibrating mass. Yani, initially, if object starts with oscillating between 2 points, by the time object loses its energy, as the energy is lost, object is starting to oscillate at a smaller distance and finally stops. So the mass spring system loses mechanical energy and eventually comes to rest. This effect is known as damping. Remember, damping is in fact a common term for the shopping. If the price of the price drops, then we say there is a damping. So damping here reserves, and if the energy of the system decreases by time, eventually system comes to rest, then that is called the damping in simple harmonic motion. So this is another important type of, maybe we should know about, the shock absorbers. Generally, we are using the shock absorbers in the car system. Bumps in the road lift the wheels off the ground and drop the driver out of control. Remember, if there is a bumps over the road, when you pass through the bump, so your car is jumping. So as the car jumps, of course, it becomes disturbs you, and you cannot continue your travel or journey with comfortable car. So then for that reason, you should solve this problem. How can we solve that? Well, a good solution is to fit the car with springs at each wheel. So right there wheel we put the springs. Why? Because as the car is passing over the bump, then car is not jumping because the tires compresses the spring. Because it compresses the spring, you don't feel the bump. However, as the spring starts to oscillate, it will continue oscillating up and down continuously. So then over the time when you are moving, your car will oscillate up and down. This also will cause you to be disturbed. For that reason, generally there is called shock absorbers parallel to the springs. So these shock absorbers are fluid-filled tubes that turn the simple harmonic motion of the spring into damped harmonic motion. So what's happening there? So there are the coils, which is the springs. Inside the springs, there are the shock absorbers. In these shock absorbers, there are fan fluid. As the car is making simple harmonic motion, these is shock absorbers. There is the liquid. The liquid is compressed. As the liquid is compressed, energy of the spring is converted to heat. Remember, if there is friction, energy of the oscillating system decreases. For that reason, these shock absorbers absorbs the energy from the coil spring, and then for that reason stops the oscillation. 1 or 2 times it oscillates and stops. So in damped harmonic motion, each cycle of the stretch or compress of the spring is much smaller than the previous cycle. Yeah, 1 or 2 or 3 times it oscillates and finally stops. This keeps the car from the continually bouncing without up and down, sacrificing the... Okay, second type of the system which makes simple harmonic motion is simple pendulum. Simple pendulum is a device which consists of a mass called a bob. It's a small ball attached with a spring to somewhere with a fixed string. So it is something like this. Assume that this is the ceiling. So you are going to suspend a small bob, which is called a small ball, which is called bob, from this string, very thin string. So this is called a simple pendulum. So this is the original position of the string and the bob. When you pull this ball or bob from equilibrium position somewhere here, and with an angle of theta, let's say. So it starts to oscillate. It moves to the other side. Again at an angle theta, stops there, and then turns back and goes there, stops there, again back and forth. Continuously, it starts to oscillate between these 2 points. So this is also a periodic motion. To some extent of this angle, it's also simple harmonic. So periodic motion, absolutely, but for the angle which is smaller than 15 degrees, so this motion also simple harmonic motion. So this device is called the simple pendulum. So first we should understand simple harmonic motion and simple pendulum are different physical concepts. One of them is the device. So this system is called simple pendulum. The motion of the bob over this path is simple harmonic motion if the angle is smaller than 15. That angle is smaller than 15. So, but this motion is completely periodic. So the force acting on the bob at any point include 2 forces. One of the forces Fg, which is the gravitational force. Second force is Ft. Now on the ball or bob, there are 2 forces, gravitational force and tension force. Gravitational force has 2 components. One of the components is Fgx on the x-axis. Fgy is on the y-axis. Fgy and Ft are in opposite direction. So these 2 forces has no effect on the motion of the pendulum's bob. But Fgx is the force which always calls the bob towards the equilibrium position. For that reason, Fgx is the restoring force here. So the bob's weight can result into 2 components. X component of the bob is the net force acting on the bob in the direction of the motion. For that reason, Fgx always pushes the bob towards the pulls the bob towards the equilibrium position. For that, as in the Fgx, and X component of the gravitational force is the restoring force. Yani Fg sine theta is the restoring force acting on the bob of the simple harmonic motion, simple pendulum. If somebody asks you what is the restoring force for simple pendulum, it is the X component or the component which is tangent. Sometimes it's defined like this: component which is tangent to the path is the restoring force, which can be calculated Fg sine theta. Fg is equal to mg, so mg sine theta is the restoring force for simple pendulum. So is the pendulum's motion simple harmonic motion? Yes, it's a simple harmonic motion if angle is smaller than 15 degrees. So this simple harmonic the simple pendulum also vibrates with simple harmonic motion if the angle is smaller than 15 degrees. So many of the earlier conclusions for mass spring system also applies here. So now let me draw again the cases. So this is the ceiling, say that this is the string, this is the ball. So the angle must be smaller than 50. But if it is smaller than the 50, so this bob starts to oscillate between these 2 points. So at the maximum displacement right here, when you pull the object up to this point, so Fgx increases, and restoring force becomes maximum at maximum displacement. Because the restoring force is maximum, also acceleration must be maximum. So, however, velocity becomes 0 because object must stop right here at the maximum displacement from the equilibrium position to turn back. If the velocity is maximum, then kinetic energy will be 0. So there will be, it's not moving at this point. Velocity is 0 at the maximum displacement. So kinetic energy is 0. However, system here has another type of energy because the pendulum's bob is initially here, then moving like this. So it's rising from the ground, from the 0 level. So because it's rising, it gains potential energy. For that reason, in mass spring system, energy is not elastic potential energy. This energy is called as the gravitational potential energy. Because at the maximum displacement, the height is maximum. For that reason, gravitational potential energy becomes maximum. But kinetic energy becomes 0 because object right there stops. Then when you release it again, when the object turns back, it starts spinning, moving faster and faster and faster. It passes from the equilibrium position with greatest velocity. If the velocity is greatest, kinetic energy also must be maximum. However, right here, because it's the zero level, the elastic gravitational potential energy will be zero right there. There is no altitude, there is no height. What about the force? Force is zero because it is at equilibrium position. It's unstable, it's a natural position. So for that reason, the restoring force is zero. If restoring force is zero, acceleration must be zero. Then object is starting to, the pendulum slope starting to rise up again. As it's rising up, of course, restoring force increases. And becomes maximum at maximum displacement from the equilibrium position. So acceleration becomes maximum because object stops, speed becomes, or velocity becomes zero. If velocity is zero, kinetic energy is zero. Because object is rising to the maximum height from the zero level, so gravitational potential energy becomes zero. So we can basically summarize all these cases. So at maximum displacement from the equilibrium position, at maximum displacement from equilibrium position, a pendulum energy is completely gravitational potential energy. So this is the zero level because at that point the age is maximum. As the pendulum swings towards the equilibrium position, and this is the equilibrium position, it gains kinetic energy, it loses potential energy. As you see, height decreases. If height decreases, potential energy decreases. So according to conservation energy, this energy must be converted to kinetic energy. So at equilibrium position, because age is zero, at equilibrium position, its energy is completely kinetic, no gravitational potential energy here. But it passes from the equilibrium position with the maximum speed and then start to rise again. As it rises, its gravitational potential energy again starts to increase. By the time kinetic energy decreases and becomes zero at maximum displacement. So if we draw the kinetic energy potential energy change, first we should know that total mechanical energy always constant because it is kinetic energy plus potential energy. Total mechanical energy is constant. Generally, this total mechanical energy depends on the height. If you lift it higher, and if you increase the amplitude of the pendulum, the elastic potential, the gravitational potential energy increases, and total mechanical energy also increases at that point. But don't forget, angle cannot be greater than 15 degrees because it is the condition for simple harmonic motion. So for that reason, at maximum displacement from equilibrium position, the energy is completely gravitational potential energy. So here, red line is pointing the gravitational potential energy. For that reason, at maximum displacement, so this is an angle. We are going to show the displacement in simple pendulum by the angle. At maximum displacement, the gravitational potential energy becomes maximum at both sides. Because object stops, kinetic energy will be zero. But at equilibrium position, vice versa. At equilibrium position, the gravitational potential energy is zero, but kinetic energy is maximum at equilibrium position. So then if you draw the graph, you are going to observe that the gravitational potential energy and gravitational potential energy and kinetic energy is changing in such a mathematical relation. So in simple pendulum, we assume that the mass of the string is negligible, must be negligible, it must be so thin. The mass is concentrated at a point, yes, it mustn't be a large extent object. The force of friction and air resistance are disregarded. So it is called simple pendulum in this case. That device is simple pendulum. But if the above conditions are not provided, it is not a simple pendulum. We say in physics it's a physical pendulum. For example, right here, it is not a mass is not concentrated at one point. So it's an extended object. This is another extended object. This is another extended object. Also, air resistance here cannot be liquidated because area is large. Air resistance here cannot be liquidated because area is large. Then we say that these three are, in fact, not simple pendulum, physical pendulum. So, sectionary questions. Which of these periodic motions are simple harmonic? A child swinging on a playground swing angle is 45. So it says periodic motion, but not simple harmonic because angle is greater than 15 degrees. A record recording on a turntable, so it's rotating. It's a periodic motion, but not back and forth motion. An oscillating clock pendulum, its angle is 10 degrees. So then, because angle is smaller than, so it's oscillating. So angle is smaller than, this is a simple harmonic motion. How does the restoring force acting on a pendulum bob changes as the bob swings towards the equilibrium position? So if bob swings towards the equilibrium position, the case is this. Initially it's here, this is the equilibrium position. So as it swings to equilibrium position, because at equilibrium position the force is 0. As you see here, the force is maximum. Force decreases. Its restoring force decreases and becomes at equilibrium position 0. So what about the velocity? Velocity right here is the 0 because object stops, but as it approaches towards the equilibrium position, velocity becomes maximum. So with the maximum speed, it passes from here and then rises again. Next question. When an acrobat reaches the equilibrium position, write this position at equilibrium. So the net force acting along the direction of motion is 0. Yes, at this position, yani at equilibrium position, the net force is equal to 0. Then if net force is equal to 0, it says that why does the acrobat swing past equilibrium position? Yani if force is equal to 0 in the direction of the motion, why is it passing? Because initially it's in motion. Remember, according to first law of motion, if net force acting on object is 0, object will stay at rest. If it is initially at rest, it will move with the constant velocity if it is initially in motion. Right here, the first acrobat is jumping from this point. So because it's speeding up, because it gains an energy until it comes here, it passing from this point with that energy, that kinetic energy, and starting to rise again. So section 2, measuring the simple harmonic motion. So first we should define what the amplitude is. The maximum displacement from the equilibrium position is called the amplitude. Now until now we defined the maximum displacement as x maximum. Now from now on we are going to say it is the amplitude, and we are going to show it by a, capital letter of amplitude. Plus a is plus x maximum, negative a is minus negative x maximum. So then the object will oscillate between the 2 points, these 2 points, so extreme points. One of them is positive a, the other one is negative a, back and forth motion over the same line. So the mass spring system, the amplitude is the amount of maximum amount of spring is stretched, as you see here, or compressed, as you see there, from the equilibrium position. So unstretched position is called equilibrium position. For simple pendulum, the amplitude is measured by the angle. So this angle will show us the amplitude. So maximum angle from the equilibrium position is called amplitude. So on the left side it is positive negative a. If we say on the right side, we are going to say it as the positive theta, negative theta and positive theta. So it is again the same as the simple mass spring system or simple pendulum. So this is the amplitude. So between the equilibrium position and the maximum displacement is the angle theta. So swinging from the maximum displacement on one side of the equilibrium position to maximum displacement on the other side and then back again is considered to be one complete cycle. So one complete cycle means we are going to start from positive A, go to the other maximum displacement, negative a, come back again, positive a, it is called one cycle. Or you are going to start from negative a, go to positive a, come back again to negative a, it's called one complete cycle. During this one complete cycle, this is one complete cycle, let's define now half cycle. Half cycle is the half of them. Yeah, an object will start from positive a, goes to negative a. Or start from negative a, goes to positive c, it's called the half cycle. What is quarter cycle? Quarter cycle is if the object moves from negative a to equilibrium position, or from equilibrium position to negative a, or from equilibrium position to positive a, from positive a to equilibrium position. All they are quarter cycles. So in one complete cycle, 2 half cycles. In one half cycle, there are 1, 2 quarter cycles, and 1, 2, 3, 4 quarter cycles there in one complete cycle. So distance traveled along a quarter cycle is a. How? From negative a to 0, or from 0 to positive a, or from positive a to 0, or from 0 to negative a. All distance traveled by the object is a. That distance is a. So a given number minus 10 centimeters, say, or plus 10 centimeters. So from 0, here is 0. From 0 to minus 10, distance is 10 centimeters. From 0 to plus 10, distance is again 10 centimeters. From 10 to 0, it's again 10. From 0 to minus 10, again It is 10 centimeter. So amplitude is 10 centimeter right there. But for half cycle, distance traveled is 2a, because say that again positive 10, negative 10, 0. From 10 to 0, 10 centimeter. From 0 to minus 10, 10 again. So 10 plus 10, it becomes 20. So if this is a, this is another a plus a, distance traveled by the object is 2a. But for one complete cycle, distance traveled is a, 1 more a, 2a, 1 more a, 3a, 1 more a, 4a. Distance traveled by the object is 4a. But displacement is different than the distance. Displacement is for a quarter cycle, from a to 0, it is a. From 0 to a, again a. So measure of displacement is from a to the 0, again a. From 0 to a, again a. But for half cycle, displacement from a to negative a is a plus a again to a. But for complete cycle, displacement for one complete cycle is 0, because object is turning back to the original position. There is no change in the position of the object. If no change, displacement will be 0. Then we are going to define what period is. The period t is the time it takes for one complete cycle. An object will start from here, goes to O, come back again to here. So you are going to count time. How long does it take? So we are going to say this is one time. This is one period. So time, period is time. Don't forget. So if one period is this is the complete cycle, then each quarter cycle is t over 4. So time from A to O, t over 4. From O to minus A, t over 4. From minus A to O, t over 4. From O to plus A, t over 4. Total time is t over 4 plus t over 4, t over 4 plus t over 4. And 4 times t over 4, which becomes t. So time for one complete cycle is t. Then for quarter cycle, it is t over 4. For half cycle, it is t over 2. If one complete cycle takes 2 seconds, so time for one complete cycle is 2 seconds, then period of this motion t is equal to 2 seconds. But if 10 complete cycles takes 30 seconds, then period of this motion, how can you calculate it? You are going to use this equation. So period is equal to total time divided by number of cycles. What is total time of travel? 30 seconds. 30 seconds. What is the total number of cycles? 10. 10 cycles. 30 divided by 10, it becomes 3 seconds. So it is the period of the this oscillation. The number of complete cycles in unit time and in 1 second is called frequency. So the SI unit of frequency is 1 over second, second power of minus 5, so these two are the same thing, or hertz. So we are going to count in 1 second how many complete cycles there are. For example, assume that if 10 complete cycles takes 1 second, so in 1 second how many complete cycles? 10. Then the frequency of this motion becomes F is equal to 10 hertz. So if 10 complete cycle takes 5 seconds, then the frequency of this motion. Now, frequency refers to number of cycles, but period refers to total time. For that reason, we are going to divide the number of cycles to total time for finding the frequency. So how many complete cycles there are there? So 10 complete cycles. 10 complete cycles in total, how many seconds? 5 seconds. So what is the frequency in this case? 10 divided by 5, which is equal to 2 hertz. Assume that if one complete cycle takes 20 seconds, then frequency. So how many complete cycles are there? 1. Total time, 20. 1 over 20 is the frequency of this oscillation, or 0.95 hertz. So the period is the time per cycle, and the frequency is number of cycles per unit time, so they are inversely related. So then if you multiply period and frequency of an oscillation, answer always 1. So this is the frequency. What is the period? Period is equal to total time divided by number of cycles. So they are inversely related, as you see. Question says, the reading on a metronome indicates the number of oscillations per unit. And in 1 minute, how many oscillations there are? So the metronome reading of the metronome indicates this. Metronome is a device generally musicians are using to play an instrument. So it gives some tick-tock, 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 tick-tock. So according to that, you play the instrument. Sometimes it's counting with small tick-tock, tick-tock for small, slow musics. For fast music which is played faster, tick-tock, tick-tock, and something like this. So what are the period and frequency of the pendulum's metronome's vibration when the metronome is set to 180? So this number says that in 1 minute there is 180 complete cycles. So number of cycles 180 cycles, but in how many seconds? It is 1 minute. So 1 minute is equal to 60 seconds. So calculate the period. What is period? Period is equal to total time. So you measure the time, total time divided by number of cycles. So then total time is 60 seconds, number of cycles 180 cycles. So answer is your the period of the motion or the vibration 1/3 seconds. But frequency is number of cycles. So then frequency defines the number of cycles per unit time. So for that we are going to divide number of cycles to total time. So the opposite of the period for that is in 180 divided by 60. So it is the 3 hertz. As you see, if you multiply these two numbers, 1/3 times 3, always answer is 1, because the period multiplied by frequency is equal to always 1. This is the relation between the period and frequency of an oscillation. Now we are going to calculate the period and frequency of simple pendulum and mass spring system. Now from the result I will start, then I am going to explain the cases. When you set a pendulum into a vibration, its period is related to by equation 2 pi root of L over G. So L is the length of the pendulum, of the string. G is the acceleration of gravity at that place. T is the period. So if period is like this, frequency will be 1/f. So 1/2 pi. So root of G over L is the frequency of the oscillation of a simple pendulum. As you see, period and frequency only depends on the length of the string and acceleration of gravity. Yeah, if you make the length longer string, longer periods. Greater free fall acceleration, smaller period. For example, when you go up to the mountain, what happens to the acceleration of gravity? Decreases. If acceleration of gravity decreases, so it is longer time of period. What does period means? So it is longer travel of time. Yeah, it's the pendulum is getting slower, swinging slower when you go up to the mountain. But if you come down, so it starts swinging faster. Faster motion means shorter time of travel, so which is the period. Yeah, and period is related to the time of travel. If it oscillates faster, period becomes shorter. If it oscillates slower, period becomes longer. So this is the equation for simple pendulum, 2 pi L over G. But now we are going to explain this according to some physical way. Two pendulums, assume there are two pendulums, L1 and L2. One of them is longer than the other one. So but the same amplitude, as you see, both have the same amplitude of theta. So their angles are equal. The shorter pendulum will have a smaller arc length to travel. Yeah, as you see, this is the shorter one, the red one. It has a shorter arc length. The green one has a longer arc length. So both pendulum have the same acceleration. How I know this? Because restoring force is the same. Restoring force is mg sine theta. If the restoring force is this, so then if we divide it by mass, we will calculate the acceleration. So as you see, mass cancels. So g sine theta is the acceleration. So because the theta is the same for both pendulum, their accelerations at that point will be the same. Accelerations are the same, but the first one will travel a shorter arc length than the second one. For that reason, time of travel of the shorter one is faster. It will move faster. So if you make the length shorter, so it moves, it completes one oscillation in a shorter time. So period becomes shorter. As you see, length is shorter, length is shorter, so period becomes shorter. If length is longer, so if you increase the length, period becomes longer. So the first one is this. Second one is, let's change this time the amplitude. To do that, we are going to use different angles, but this angle mustn't be greater than the 15 degrees, remember. So it is the condition for simple harmonic motion. When the amplitude of the pendulum increases, now this is the one of the pendulum, so this time we are going to keep the lengths are equal, because you cannot determine the two variables at the same time, how it affects the oscillation. For that reason, we choose two different pendulums at equal length, but only their amplitudes are changing. So then if amplitude is changing, the arc length of the first one, green one, is shorter than the arc length of the red one. But acceleration of the green one also smaller than the acceleration of the red one, because g sine theta 1 is smaller than g sine theta 2. Why? Because theta 2 is greater. So delta S1 is smaller than delta S2. So distance traveled will be shorter. However, acceleration is also small, so then time of travel for this one and that one will be the same. And if you release these two pendulums, these two bobs from these positions, when this pendulum comes here, the other one will also reach there. For that reason, their periods are independent from the amplitude. And amplitude of the oscillation does not affect the pendulum. In fact, you can see that in the equation there is no amplitude. There is L but no amplitude. Also, we can explain it by this way. Third one is the mass. So then we use same amplitude, same length, but masses are different. So if masses are different, of course, restoring force will be different, because greater mass will have a greater restoring force, m1 g sine theta. However, to find acceleration, you should divide mass again. Mass and mass will cancel. Acceleration will be g sine theta for the greater bob in mass, greater mass or smaller mass. So the bob will have the same acceleration. So arc lengths are the same, accelerations are the same, so that time of travel also will be the same. For that reason, mass has no effect on the period of the simple pendulum. Also, there is no mass in your equation. So period is independent of mass, period is independent of the amplitude, but period is dependent to length. And in general, we can say that changing the length of L of the pendulum does affect its period. A change in the free fall acceleration also affects the period of the pendulum. So the exact relationship between these variables is t is equal to 2 pi L over Ag. So calculate the period and frequency of a 3.5 meter long pendulum. So length is equal to 3.5 meter at the following locations. So G is given as 9.832 meter per second squared. So calculate the period. Use the equation t is equal to 2 pi root of L over G. So L is given, G is given. You are going to write them and calculate it. So I'm not going to solve it. You can solve on your own. Another one is a trapezoid artist swings in simple harmonic motion with a period of 3.8. So this time period is given 3.8 second. Calculate the length of the cable supporting the trapezoid. So we are going to calculate the length. L is the question, but we know the acceleration of gravity is 9.81 meter per second squared. So this time T is equal to 2 pi root of L over G. To calculate the L, you should first square the both side of the equation. So T squared becomes 4 pi squared times L over G. Cross multiply them. So 4 pi squared L is equal to T squared times G. You are going to calculate the L, divide by 4 pi squared, divide by 4 pi squared, so they will cancel. So L will be equal to T squared G divided by 4 pi R squared. So then you write the numbers and you can calculate the length of the pendulum. So questions are basically like this. The next question is also the same as the previous one. You need to know the height of the tower. So height of the tower, but the darkness obscures the ceilings. You cannot see how high it is. You do note that the pendulum extending from the ceiling almost touches the floor. Yani length of the pendulum is equal to height of the tower. So when you find the length of the pendulum, you are going to understand what height is. So its period is 12 seconds, so it's swinging, so you count the period as 12 seconds. How tall is the tower? Calculate the length of the pendulum. So G is equal to 9.81. So again, you are going to use the same equation, and you will find by this way the length of the pendulum, which is equal to height. So another question, it says that the free fall acceleration on the surface of the moon is approximately 1/6 of the free fall acceleration on the surface of the Earth. Yeah, if we say on the Earth is AG, on the moon it will be AG divided by 6. Compare the period of the pendulum on the Earth with that of the identical pendulum set in the motion on the moon. So identical means their lengths are equal. So I'm going to write the equation for pendulum on the moon, period of the pendulum on the moon, period of the pendulum on the Earth, 2 pi L over AG over 6, because acceleration of gravity on the moon is Earth divided by 6, AG is Earth divided by 6, but for Earth it is 2 pi L over G. 2 pi will simplify, so this must turn upside down, AG over 6, it becomes 6 L over AG. So because in your equation you can get this 6 out of the root by root of 6. So root of 6 L over AG divided by L over AG. So this will cancel to you. So answer will come 0 over 6, which is 2.45. What does it mean? The period of the pendulum on the moon is 2.4 times times of the period of the identical pendulum set in the motion. Yani the pendulum on the moon is 2.45 times slower. So by a factor of 2.45, the pendulum on the Mars is slower. If on the Earth the same pendulum is oscillating like this, on the moon it oscillates like that. So it is pendulum is smaller, so period is longer. Why is the pendulum is reliable timekeeping device, even if its oscillation gradually decreases in amplitude over time? Because we know that period is independent of the amplitude. If angle is smaller than 15 degrees, the period of the pendulum is independent of the amplitude of the motion. For that reason, if its amplitude is great or small, it doesn't make difference. It will move the same, it will measure the correct time because period will not change. In mass simple system, there is a mass, you know, there's a mass, there's a spring. Spring constant is K, mass of the object is M. So the equation for, now I'm going to just quickly give the equation at the beginning. So the equation for period is 2 pi M over K. So as you see, period depends on mass and spring constant. Nothing else can change the period of the simple mass spring system. Frequency is what? 1 over 2 pi root of K over M. So then now we are going to get this equation from the by using some physics. So assume that first, let's get the mass. Mass in the how mass determines or affects the period of the simple mass spring system. Assume that a heavy object is connected to the spring. So remember, restoring forces F is equal to minus K times X. As you see, restoring force is independent of the mass. Restoring force only depends on K and X. So, but if you use a greater mass, because restoring force this is constant, if you increase the mass, acceleration of the object decreases. So object accelerates slower. If acceleration becomes slower, average speed the object is moving decreases. Average speed, yani from the maximum displacement to the equilibrium position, average speed is smaller. Smaller average speed results a longer time of travel. So then if the longer time of travel, so amplitude becomes longer. For that reason, greater mass means greater time of travel, greater period. But if you change the spring constant, and greater spring constant K, because the restoring force is proportional to K, if you increase the K, restoring force increases. But acceleration because you divide to find the acceleration, you divide it by mass, but mass is constant. We didn't change the mass. For that is an increasing spring constant increase the force, increasing force increase the acceleration, increasing acceleration increase the average angular speed. Average angular speed, if increases, it travels in a shorter time the distance. So then, if the time of travel is shorter, so period becomes shorter. For that reason, if you increase the k, according to the equation t is equal to 2 pi m over k, if k increases, period decreases. Now then we can say that as stiffness increases, the period of the vibration decreases. Amplitude. So if you increase x, force increases, yes, but acceleration also increases. If acceleration increases, average speed also increases, but average speed increases. However, because you increase the distance also increases. Two increasing quantity cancel the effect of one another, so delta t is independent of the increase in the amplitude. And also in your equation, t is equal to 2 pi m over k, there is no amplitude. So for that reason, amplitude does not affect the period of the oscillation. Don't forget, amplitude does not affect the period of the simple harmonic motion, simple pendulum, also does not affect the period of the mass spring system. So this is the equation for calculating the period of mass spring system. Two mass spring systems vibrate with simple harmonic motion. If the spring constant of each system are equal, and mass of one of them is twice that of the other one, which system has a greater period? Of course, the one with greater mass will have a greater period. Of course, we should know this because period is directly proportional, increases with increasing mass. A spring of spring constant 30 Newton meter, so K is equal to 30 Newton per meter, is attached to different masses. The system is then set in motion. Find the period of the frequency of the vibration for the masses following magnitudes. One of the masses, the first mass is 2.3 kilograms, so calculate the period. So period of the equation is 2 pi m over k. Then you are going to write m here, k here, then you are going to calculate the answer. The body of 1,275 kilogram car is supported on the frame over 4 springs. Remember, there are 4 wheels, 4 wheels, and 4 springs are located just near the wheels to oscillate to make the car comfortable. 2 people riding in the car have the combined mass of 163. So 2 people, but mass of the car also included. So total mass in this case will be 1,428 if you add them. Total mass. So when driven over a porthole in the road, the frame vibrates with a period of 0.84 seconds. So period of the oscillation is 0.84. For the first 3 seconds, the vibration approximates simple harmonic motion. So you can use the equation for simple harmonic motion to calculate the period. So find the spring constant of a single spring. We will calculate the springs, but first we should calculate equivalent. Yani first we will find the spring constant of 4 of them. After that we are going to calculate the spring constant of the one of them. So period is given 0.84, 2 pi 6.28. Mass total is calculated 1,428 divided by equivalent. So if you continue calculation, equivalent spring constant will be almost 80,000 Newton per meter. But this is 4 of them. 4 spring has this equivalent. To calculate this spring constant of one of them, you should divide the equivalent by 4. So 80,000 divided by 4, it's almost 20,000 Newton per meter. It is the spring constant of one single spring. 0.75 kilogram mass attached to a vertical spring. So mass is equal to 0.75 kilogram. So it's attached to from a vertical spring. So initially the spring is something like this. Then you attach this spring to an object. Of course, it stretches. So because there is an Fg, gravitational force. So what is the spring constant? It says, so spring constant can be calculated because it's stretched by a distance of 0.3. X is equal to 0.3 meter. So calculate the spring constant. So Fg divided by X is equal to K. So Fg is equal to mass times gravity. So K becomes mass times gravity divided by X. Mass is 0.75. Gravitational acceleration is 9.81. So divided by x is 0.3 meters. So answer will be K. The mass spring system now is placed in horizontal. So the same system will put now in horizontal. Then you are going to this equilibrium position. You are going to then set into vibration. And how? By a little pull and releasing, it starts to oscillate like this back and forth. So calculate the period. Period is equal to 2 pi m over k. M is known. This is 0.75. K you just calculate here. You are going to write the number there, and you will find the period of the oscillation. Okay, this is all about the section 2.